Hello. So today we're talking about solving equations. Particularly, we're solving exponential equations and logarithmic equations. So with exponential equations, there are two type of problems you guys might see. Those are um, equations that have the same base. So, for instance, if I say 5 to the x equals 5 to the um, 21st power. If I had something like this, the bases are all the same. I just have to figure out what x has to be. Or type 2 is where the bases are not the same, but they could possibly be. So for instance, let's say we have 32 equals 8 to the x power over 16. So the bases are not the same, so we have to do extra step or two. All right, so this first problem, the bases are the same. I can combine this side because when you multiply powers, you add the exponents, right? So this is 5 to the 21 plus 3x. So now there's a general rule. If b to the x is equal to b to the y, this implies that x is equal to y. So if the bases are the same, these exponents also have to be the same. So all we're going to do is we're going to take these two things and set them equal to each other. So once the bases are the same, we set the exponents equal to each other. And then from here, we're just solving this equation. So we want to get all the variables on one side and get all the integers or numbers on the other side. So we get negative 2x equals 21 and just divide by negative 2. So we get x equals negative 10.5. Or you could have left it as 21 over 2. I'm fine with that as well. All right, so problem type 2, we write this as something, or 32, we can rewrite 32, 8, and 16 all as powers of 2. So 32 is the same thing as 2 to the 5th. 8 is the same thing as 2 to the 3rd power. And 16 is the same thing as 2 to the 4th power. So now this equation becomes 2 to the 5th power equals, so when we multiplied over here, we added the exponent. So when we divide, we're just going to subtract the exponents. So we'll get 2 to the 3x minus 4. So now the bases are the same. So we've manipulated our problem to get it to look like something we know how to do. These bases are the same. The bases are the same, the 2's. So that means these exponents have to be equal to each other. So 5 has to equal 3x minus 4. And then we just solve this. And x equals 3. So those are the two type of problems you'll see on Alex. There is a third scenario that I'm going to go over in the next slide. All right, so we're going to talk about how to solve exponential equations with unlike bases, or bases that cannot be made to be the same. So if we look, 5 to the 1st power is 5. 5 to the 2nd power is 25. And 5 to the 3rd power is 125. So 5 to what power will give us 29? Well, 29 is kind of close to 25, right? Which means this number should be close to 2. It's between 2 and 3, we know that. but it might be 2.1, 2.01, 2.05. But we can't just guess and check. Well, you can, but it'll take literally forever. So we're going to go ahead and solve this with logarithms. So when the bases are not the same, you take the log on both sides. Notice I'm using log base 10, mainly because log base 10 is in your calculator. You can use other bases as well, but it just depends on the problem. 99% of the time, you're going to use log base 10 with these kind of problems. So now, why did we do this? How does this help us? Well, we can use the power property of logarithms. So we can use this property, which states any exponents. So this exponent, I can multiply, I can bring down in front and multiply by my logarithm. And this is a 1. There's a 1 up here, imaginary 1. That's not going to change anything if I multiply it. So we use the power property. Now that helps us because we don't have any exponents. We're just solving for x. And this log 5 is just a number. So the same way we would solve x times 3 equals 9, we would solve this. These two things are just numbers. So we're going to treat them as if they're numbers. So we're going to divide both sides by log of 5 to get x by itself. And then you put this in the calculator and you get approximately 2.09. So if I do 5 to the 2.09 power, it'll give us close to 29. Okay, let's look at example 2. Now this problem's a little bit more challenging and we have to incorporate some of the things we've already seen in the video and previous videos. So first thing, when I'm seeing this problem, first thing I want to do is I want to get this combined. I want to manipulate this to look like a problem that I've done before. So I know I can rewrite 16 as a power of 4. So I'm going to go ahead and do that. So we get 4 to the second power raised to the x plus 3 times 4 to the x. So now if we take a power to a power, so this 2 raised to that, we multiply. When we multiply this out, we get 2x plus 6. Notice we have to distribute to both terms. And then also, this, when we multiply these two things here, we add the exponents. So we're just going to add this x on at the end. So now we have some number raised to this power, 3x plus 6, equals some other number. The bases are not the same. The bases are uncommon. They can't be made to be the same. So now, just like the last problem, we take the log on both sides. So log of 4 to the 3x plus 6 power equals log of 521. So now we use our power rule, which says that we can take this exponent and bring it in front. So 3x plus 6, that whole quantity, times log of 4 equals log of 521. And then we can divide by log 4 on both sides. We get 3x plus 6 equals log of 521. over log of 4. And then we just solve this. So we're going to subtract 6 and then divide by 3. So we will get x equals log of 521 over log of 14, or 4, I'm sorry, minus 6, that whole thing divided by 3. So we're going to put this in the calculator. And what we get is approximately negative 4 or negative 0.496. So this means if I plug in negative 4.96 to my x, I should get 521. If I plug it on the left side, I should get 521. So let's check that. So 16 to the negative 0.46, negative 0.496 plus 3, 16 raised to that power, times 4 to the negative 0.496 should be approximately 521. And when I put this in the calculator, you get 520.59 approximately. So because we rounded our answer, we get close to 521, but this is good enough. So we know that this answer is correct.